What you're about to learn is used all the time, from other courses you take to your everyday life. You're about to begin to learn how to predict what will happen to an object when it falls, collides, accelerates, and more. Look around. The world is full of moving objects. Think of sports, transportation, military. Even as you sit in your chair right now, you are hurtling around the sun faster than you can imagine. In this video, we will look at how things can move back and forth in a straight line, and this is called one-dimensional kinematics. Let's start by looking at a red plastic ball. Right now, the ball isn't moving, so we can say it has constant position, denoted by x. Let's call this point the starting point, or position equals 0. We can use this ruler to keep track of position. Although the ruler uses centimeters for its units, the rules you're about to learn apply no matter what units we choose to use. If we drop another ball somewhere else, we can compare the locations of the two balls. This new ball has a constant position equal to positive 5 centimeters, because it is 5 units to the right of the origin, at 0. And since we've set up the ruler so that balls to the right of 0 have positive position, this means that balls to the left of 0 will have negative position. So let's define position as the number describing the location of an object compared to the starting point, which we can choose. But what about if we want to move the original red ball to a new position? To do this, we'll have to talk about a few new ideas. Distance tells us how much ground the ball has covered since it started moving. Notice how any movement of the ball adds to the distance. Displacement tells us how far the ball ends up compared to where it started from. Look at how when the ball gets closer to 0, displacement goes down, but distance is always increasing. So we can see that the distance tells us how far we have traveled, but gives us no information on where the ball is at any time. While displacement tells us where the ball is, but on its own doesn't tell us much about how far the ball has really traveled in the past. The differences between displacement and distance are so important that scientists came up with 2 words to describe these differences: scalar and vector. Distance is a scalar because it is just a number, and it only tells us how far the ball has gone without any info on which direction it moved in. A scalar is just a magnitude. Displacement is a vector, because we can tell the difference between when the ball has moved left or right. The vector quantity tells us both magnitude and direction. Here's a trickier one though. What about position? Well, first let's ask ourselves this: does position have a magnitude? This one's a bit of a freebie. Position is represented by numbers, so of course it has a magnitude. But what about direction? We have to think carefully. We know that position can be a negative number too, and we already saw that negative means left in one dimension. So then position has both a magnitude and a direction, so it has to be a vector. Okay, so when we are dealing with one dimension, it can be hard to tell the difference between a scalar and a vector. So let's quickly take a look into a 2-dimensional example. Imagine a runner going around a track. As the runner goes around, the total distance is simply the length of ground the runner has covered, and is shown here in green. The total displacement is the straight line change in position from where the runner started, shown in blue. We don't need to show the exact numbers here, it's just the length of the lines that matter. In one dimension, we usually just keep track of the direction of the displacement with a positive or a negative sign. In 2 dimensions, we can use angles, compass directions, and more. After the race, the runner has traveled a distance of 1 lap, or 400 meters. The displacement of the runner, however, is 0, because the runner ended up at the exact same position as it started at, so there is no change in position after 1 lap. Now that we have a clear picture of distance and displacement, we can get into some juicier ideas. If we want to change the position of the ball, time needs to pass, and with all this background theory, we can now look at the idea of velocity. In day-to-day life, you have probably heard people talk about the speed of an object rather than its velocity, but what's the difference? Well, speed is a scalar quantity, while velocity is a vector quantity. This means that speed only tells you how fast an object is going, but velocity tells you how fast the object is going and its direction of motion. But what does this mean? In one dimension, the only difference you will see is that velocity can be positive or negative, while speed will always be a positive number. And because of this extra information on direction, velocity is used most often in all physics calculations. Now let's look more closely at the math behind velocity, since there is a very good chance that this will be on your tests or exams. If there is a change in position with a change in time, then we can say that the ball has velocity, and we can turn these words into an equation. Delta x over delta t is equal to v. And notice how here we are showing vector quantities with lines over the symbols, but you might also see this shown in a different way, such as with symbols in bold. The simplest case is when the ball moves with constant velocity. You may be wondering why we are graphing position and not displacement here. They are equal in this case, since we're talking about total displacement. But be careful, this isn't always true, since you can talk about the displacement between any 2 points you want. Let's take a look at what constant velocity looks like. We can see that the position changes by the same amount for every time interval by looking at the position graphed against time. It is a straight diagonal line. What then would the velocity graph look like in this case? One trick you can use to predict what the velocity will look like is to calculate the steepness, or slope, of the position time graph. To calculate the slope, we can just look at the rise and divide it by the run. Let's try it out. We can see that the rise is going to be equal to 30 centimeters, since we start at 0 and end at 30. But now look at the run. We are starting at time 0 and run the experiment for 10 seconds. So the run is 10 seconds. 30 centimeters divided by 10 seconds is equal to 3 centimeters per second, which is the velocity. We found the velocity just by looking at the slope of the position versus time graph. So why are we allowed to only look at the starting point and ending point and forget about everything in the middle? Well, this is because the slope, or steepness of the line, never changed. It's a straight diagonal line from start to finish. No matter what part of that straight line we look at, the slope is always the same, so the ball must be traveling at constant velocity. Let's see what the velocity graph looks like now. It's a straight horizontal line. To make things easier to see, let's stretch out the time axis. But now let's speed things up and see what happens to the graphs. Consider how the slope of the position graph is steeper, and the value of the constant velocity becomes larger. Let's try that again with an even faster ball this time. It's even steeper now. So when we look at the slope of the position graph, we can figure out the velocity of the ball. But what about when we look at the slope of the velocity graph? Well, it turns out that we can actually figure out the ball's acceleration, represented by the formula delta v over delta t is equal to a. And since the rise here is 0, and 0 divided by any run of time is 0, we know that the slope must be 0. We never gained any velocity as time passed, so the acceleration is therefore constantly 0. But if the ball is a changing velocity with passing time, then the ball must be accelerating. Now we're going to have to look at an entirely different example. Let's look at a ball falling to the ground in a straight line, because we are still dealing with one-dimensional kinematics. It has constant acceleration due to the force of gravity. In many cases, it is useful to define down as negative and up as positive. Here we will call down positive to stay consistent with our earlier graphs, but keep in mind that either can be used based on the conditions of the problem. If we drop the ball from rest, the ball will start with zero velocity and gain a certain amount of velocity every second, since we are now dealing with constant acceleration. So let's see what that looks like. Unfortunately, that was a bit too fast to actually learn anything, so let's slow things down a bit. Now we can see how the acceleration graph is a flat, horizontal line, just like we saw for velocity when it was constant. This is going to be key for all problem solving you will do in high school physics. You can always assume that acceleration is constant when only gravity is acting on your object. What about the velocity of the falling red ball? What would its graph look like? To answer this, we can learn a new technique, similar to the slope method we learned before. This time, instead of going from position to velocity and velocity to acceleration, we will use the area trick to do the reverse. The trick is that the area under the acceleration graph up to any point is equal to the velocity of that same point. So let's try it out. What is the velocity at 0.2 seconds? In the acceleration graph, we have a rectangle, so we could find the area by simply multiplying the base by the height. In this case, the base is 0.2 seconds, and the height is 9.8 meters per second squared. So we can do 0.2 multiplied by 9.8 is equal to 1.96 meters per second. Let's check our result against the experiment. Excellent, we were right. Let's do one more point, but visually instead of using calculations. Let's take a point halfway into the experiment, since we just need to find the area under the graph, and we can see that this looks like it is half the area under the line. Then the velocity at this same time must also be half of the first value we found, at 0.2 seconds. Just looking at the graph shows that we were right. So now we know that if we did this enough times, we could calculate enough points on this velocity graph to get a pretty good idea of what the whole graph looks like. Now that we've looked at how to find the velocity graph from the acceleration graph, there's only one more step to do. As you can probably imagine, we can use the same trick that we've just done to find the position at any given time. To find the final position, we'll have to find the area under the line again, but this time, it's a different shape. We have to be careful with this. We can't always just multiply the base times the height like we did last time. We have to take into account the shape of the area under the line. As you may already know, for a triangle, the area is equal to 1/2 multiplied by the base multiplied by the height. And since we are finding the final position, we look at the final time and the final velocity. In this case, we have 1/2 multiplied by 0.2 multiplied by 1.96. Which is equal to approximately 0.2. Wait a minute, it looks like our final position should be 20, not 0.2, just by looking at the ruler. This is a very common mistake. We didn't think about units. If we think about units, we realize we are actually correct. We should have included units in our calculation from the start. 1/2, which is unitless, multiplied by 0.2 seconds, multiplied by 1.96 meters per second, and dividing out the seconds leaves us with 0.2 meters, which is equal to 27 meters. So let's go ahead and do the same thing as last time. Let's try to find the position of the ball halfway into the fall, but only visually instead of calculating it. This time the area of the triangle formed looks smaller than the area of the second half of the graph. So it looks like this time the position graph might not be a straight line. But then what would it be? Let's run the experiment again and find out. You may have talked about this in your math class. The shape of this graph is called a parabola, and is what the position-time graph looks like for a free-falling object due to gravity. You can relax now, we are almost done piling on new information. Let's look at all the graphs we've made so far, and just reflect. The first thing we looked at was a ball resting with constant position. We then looked at a ball with constant velocity. By using the slope method, we saw how from only the position time graph, we could figure out what the velocity and acceleration graphs look like. Now we have just finished looking at constant acceleration, and learned that by using the area under the line method, we could work backwards to determine what the velocity and position graphs must have looked like. When finding the velocity of an accelerating object, there are two different types that you should know about: average velocity and instantaneous velocity. As you will find out now, it mainly makes sense to talk about these when an object is accelerating, because it is only then that you will be able to distinguish the two. Let's look at the velocity graph. If we want to find the average velocity, our first question should be, over what time interval? As an example, we might want to know the average velocity from the start to the end of an experiment. In the case of our falling ball, this means that the average is our initial velocity plus our final velocity divided by 2, or 1.96 meters per second plus 0 meters per second, all divided by 2. So the average velocity from start to finish was 0.98 meters per second. If we want to find the instantaneous velocity, we look at how far we traveled over a tiny amount of time, at essentially 1 instant. If we are looking at the velocity time graph, this just means picking off the value on the velocity axis for any single value on the time axis. It only takes one step. For example, at 0.15 seconds, we find that the instantaneous velocity is 1.47 meters per second. But what if we only had the position time graph? To find the instantaneous velocity at 0.15 seconds, we have to figure out the slope at that instant. And to do this, we'll use something called a tangent to the curve. Luckily for you, you already know what a tangent is, but you just might not realize it yet. See, a tangent is a line formed at any point on a curve with the same slope as the curve at that point. For all the graphs shown here with straight lines, there is not much point to using the tangent technique, because we can easily see what the slope is at any point and calculate it in one step. But for the position time graph for a free-falling ball, it isn't so easy, and requires 2 steps to calculate the instantaneous velocity from just the graph. Step 1 is to draw the tangent to the curve. But how do we do that? Well, unfortunately for now, you will usually have to just eyeball it. However, there is one trick that can help you visualize it. Imagine if we could just zoom into the position graph at 0.15 seconds and see the instant more clearly. And now we can really see it. The parabola does look like a straight line. And we didn't do any tampering here, we only zoomed in. And of course, drawing a tangent on a straight line is a simple process. So now when we zoom back out, we can see that we have found our proper tangent at 0.15 seconds. And to complete the second step, we now just find the slope of that tangent, and voila! We have found our instantaneous velocity, without even looking at the velocity time graph. So let's make sure we got it right. We find that the instantaneous velocity at 0.15 seconds is 1.47 meters per second. Exactly the same as what we just found by using the velocity graph. You might not realize it, but what we have just done is actually the basis of a type of math that everyone is afraid of: calculus. But don't worry, you won't need to know much about this in your introductory physics classes. So we have finally now covered all the most useful examples for one-dimensional kinematics. Although it might have seemed like we only covered some simple motion, you will find that as you learn more about physics, you will see problems where it is useful to manipulate more complicated situations into looking like these few linear cases.